Now that we've introduced the basics of our switching power supply and its power consumption, let's look at a quick example to compare the power consumption of a linear voltage regulator and a switching power supply. So for this example, what we're going to want to do is we want to take a VRAW of 10 volts. So we want to go from VRAW of 10 volts to some lower voltage. V out equals 5 volts, and we're saying that that particular voltage, the load, is pulling 3 amps of current. So what we want to do is we want to compare our linear regulator and our switching power supply. Okay, so first let's take a look at our linear voltage regulator. So I've copied here a circuit that we've looked at previously, so this was our discrete circuit. And so of course what we're saying then is we have 10 volts for our V raw over here on the left. Our V out, we're saying we want that to be 5 volts, and we're saying that when it is pulling this 5 volts, or when it has 5 volts, it's pulling 3 amps of current. So we can find the approximate power dissipation for this transistor, Q2, which we said is sort of our main component of this regulator. Of course, there are various components, but this is where our sort of excess power is going to be consumed, and we're going to see why this is less efficient. So in order to help this discussion, what we can define is a voltage across here of VCE2. So VCE between our collector and emitter on Q2 here on the top. And we make a couple assumptions again. Like always, we can say the power in our transistor is going to be approximately that collector emitter voltage times our either collector or emitter current if we're neglecting base current. So we can say power in our transistor is going to be approximately VCE2 times I of our transistor. And so we can call that IE, for instance. And so that would just be our current right here. So our emitter current. Okay, so now we can make another assumption, and we can say, well, the voltage being pulled down through this voltage divider network should be pretty small, so that we can say that this is approximately VCE2 times the load current IL. And now we just have to plug in the values. So from a simple KVL across the top, we can see that VCE2 is going to be the 10 volts on the left minus the 5 volts on the right. And of course our load current is the 3. So we see that this power for our transistor is 15 watts. So again, that's approximate, but that's going to give us a good first order approximation. So we expect this to be improved upon in our switching power supply. So let's take a look at our average power dissipated in our switching supply and compare it to this transistor in our linear regulator. So I've copied a couple of our important equations for our switching power supply. So these two equations are from our previous video. We found our average power dissipated is equal to this term here. And we also defined this fractional switching duty cycle, ds, as defined here on the screen. So with our switching power supply, what we're going to want to do is we're going to want to set this ds, our fractional switching duty cycle, to 50%. And so that's because our output is, of course, 50% of the V raw. So we're going from 10 volts down to 5 volts. And so let's just say, so this is 50%. So our average output is V out. And so if we're switching, sort of our two states are going to be all of the voltage, which is 10, or none of the voltage, which is 0. So our average of that is, of course, going to be 5. We multiply that, or sorry, we're either 10 or 0. So we're multiplying that by our fractional switching duty cycle to get what our average is. And so in this case, multiplying by that 50% is going to give us 5 volts. We can kind of consider our two extremes. Of course, if our fractional switching duty cycle was 100%, we just have the full 10 volts, we wouldn't be switching. The other extreme would be 0. If we're not switching at all, we'd of course just have 0 volts. So in this case, because we're stepping down by half, we choose that 50% fractional switching duty cycle. Okay, so now we need to consider our energy conservation. And we're going to use this principle to determine our maximum load current. So we want to find the current during on period, which is going to correspond to our our I max. So we can see that in some of the plots that we had in a previous video. And so what we can say is that our I max is equal to that average output current divided by our DS. And so if we're multiplying our average output voltage by the DS, we are dividing by the current such that the power is the same on the input and the output side. So here we have that 3 amps divided by our 0.5, and we get 6 amps for I max. So let's put in some typical transistor values so that we can plug into this P-dis equation. So let's say for typical transistor, we have a minimum voltage, Vmin equals to 0.7 volts. We have TS on, so that's sort of our on time when we're ramping up, is equal to 6 microseconds. Our TS off is equal to 12 microseconds. And so this is the type of information that you could find on the data sheet for the transistor. It might vary depending on what frequency you're operating it at, but this information should be there. So we can also select a switching frequency. And so this is again going to depend on your particular application, and we'll talk about sort of why this higher frequency is useful here in a little bit. So let's say we select a switching frequency of 20 kilohertz. Well, we can just invert that. 1 over 20 kilohertz is going to give us our switching period, which is equal to 50 microseconds. So with all of this information, we now have enough to plug into that power dissipated equation. But before we do that, I want to draw sort of our waveform for our current so we can better understand what's going on. So let's draw here our current versus time. Okay, so we have time here, and let's do our time in microseconds since everything is in microseconds. And here is our current as a function of time. Our key value is going to be our I max. And some key values we're going to have here, and I'm going to do my best to make this close to scale, but it's not going to be exactly to scale. So let's say we have, well, let's go ahead and do this. Let's say we're going up to 50 because we know that is our sort of our period. So we're going up to 50 microseconds based on this TS. So roughly halfway in between there we have 25. And then let's say somewhere around here we have 6. And somewhere around here, say we have 37. And so we'll see why those are relevant numbers here in a second. So basically what we want to do is we want to focus on these values right here. And of course this right here, and our duty cycle, fractional duty cycle of 50%. Okay, so we know that our overall period is the 50 microseconds. So if we start here at 0, we say we should begin to be repeating once we get to 50 microseconds. So this is our overall period. Now we know that our on switching time is 6 microseconds. And again, this information would come from a data sheet, for instance. So let's draw here. So from 0 to 6 microseconds, that's the time it takes for us to go from 0 current up to our I max, which we said was 6 amps. And so we can just draw a little dashed line to indicate that we've gotten up to our I max. So now we're going to go for a certain amount of time. And what is that amount of time? Well, we can figure that out based on the equation for our fractional switching duty cycle. So we know that is supposed to be 50%. And looking at this equation, we know that our TS is 50 microseconds. We know our TS on is 6 microseconds. And we know we want this DS to be 50. So we can solve for our T on right there, the only thing not highlighted in that equation. Another way to think about it is if we want DS to be 50, and we know TS we want DS to be 50%, and we know TS is 50 microseconds. We want the combination of TS on plus T on to be 25 microseconds. So either way you want to think about that, what we're going to end up having is this switch staying on until we get to this 25 microsecond. So we get something that looks like that. And so that's based on our 50% fractional switching duty cycle. So now we come back up here, we notice that our switching off time is 12 microseconds. So 12 plus 25 is going to give us 37. So we take 12 microseconds to get back down to zero current. And then we stay at zero current until we get to 50, and then that's our period. And then we just repeat this process over again. So then we're increasing back up towards our I max. So that's what our switching waveform would look like. So now let's plug all these values into our PDIS equation and see what we get for that value. So our P dissipated is equal to our switching frequency, which is 20 kHz, times our I max, which is 6, and then all of that is multiplied by. So now we're going to have, and so again, let me just point out, we're using this equation up here on the top of the screen. So we have our T on, and remember this is going to be our T on here, which it turns out is 19 microseconds. So we have 19 times 10 to the minus 6 multiplied by our V min, which was 0.7 volts, so that was given as sort of our standard transistor, our typical transistor value. We then add terms for our on and off switching. So we have 6 for our on switching plus 12. Both of those are micro, so I'm going to multiply by 10 to the minus 6. And notice I'm taking everything back to base units just to kind of be safe here. We're multiplying that by 10 and dividing by our I max of 6. And so coming up here we can see our 10 is our V max, that's our V raw, and the 6 just came out of our math, so that's not our I max there. Okay, so we plug this in and we get that our power dissipated is 5.196 watts. And so we can compare that then to our approximate 15 watts of power dissipation for our linear voltage regulation. So we have a much improved power consumption, and we haven't even tried to optimize this design. So improved power consumption with a non-optimized design. And so what do I mean when I say non-optimized design? Well, like we talked about in our last video, we can come in here, we can look at the part of our power that's due to our on time and the part of the power that is due to our switching. And based on that, we can choose a transistor such that one of these terms is dominated. And maybe if we have really fast switching, we want to choose it such that we have a minimum voltage, so that basically we sort of minimize this equation here, where our switching would be minimizing this, and choosing a transistor with V min would be minimizing this term. So we can sort of do better than this 5 watts, but even with just choosing typical transistor parameters, we see that the power dissipation is a lot better than in our linear regulator. One other thing to note is we would also need additional filtering, because now we have this 20 kHz switching signal. So additional filtering. But one thing to note is that our 20 kHz, which is the frequency of this switching, is going to be much easier to filter than the frequency of the power on our AC line, for instance. So much easier to filter than our 50 or 60 hertz frequency of our AC power line. And so if you recall, what we talked about frequency or filtering these frequencies sort of with our brute force method is we have a capacitor and we have whatever the current is, but that's capacitance is inversely proportional to our V ripple as well as the frequency of our ripple. So here we're talking about this frequency, so if that frequency is much higher, of course our capacitor needs to be a lot lower, and so that's a lot more feasible to do at high frequencies.